Hi, welcome back. Before jumping into Kepler's third law, let's have a look at how we send spaceship to Mars. The Earth is moving in an elliptical orbit about the Sun. Mars is also moving in an elliptical orbit about the Sun. How do they manage to send a spaceship from the Earth to Mars? Well, based on many movies, you just grab your ship and drive it there. The problem is that this requires an immense amount of fuel, and fuel is not only expensive but also heavy. So your ship is heavier, and you need even more fuel to move that fuel. The smart thing to do is to use Newton's first law, inertia. Once you reach the speed you want, because there is no friction in space, you just let the ship move. But first you need to jump from one orbit to another. Objects in space move following circles, ellipses, parabolas, and hyperbolas. When you send a ship from Earth to Mars, it is first on the Earth, so it is moving in an elliptical orbit, close to a circle. You want to transfer it to another elliptical orbit, that of Mars. You use slingshots to do those orbit transfers.
And right now, the Hermes is headed towards you, starting its month-long deceleration to intercept. But instead, what I'm proposing is we start accelerating immediately to preserve velocity and gain even more. We don't intercept with Earth at all, but we come close enough to get a gravity assist and adjust course. While we're doing that, we resupply with the probe,
The Taiyang Shen.
pick up whatever provisions we need, and now we're accelerating towards Mars. You're Mars. Now, we're going too fast at this point to fall into orbit, but we can do a flyby.
You push the ship so that it goes into a long transfer elliptical orbit. This orbit needs to cross Earth's orbit but also Mars' orbit. The transfer orbit will be such that its perihelion will cross the orbit of the Earth and its aphelion will cross the orbit of Mars. Of course, because you want to land on Mars, the planet needs to be at the aphelion of the transfer orbit right when the ship is going to travel half of the transfer ellipse, from its perihelion to its aphelion. If R1 is the radius of the orbit of the Earth and R2 is the radius of the orbit of Mars, then the semi-major axis of the transfer ellipse is 1/2 of R1 plus R2. We call this A. We give a sharp push to the ship so it leaves the original Earth orbit and enters into the elliptical transfer orbit. The gravitational pull from the Sun will make the trajectory of the ship be an elliptical one. Once the ship is at the orbit of Mars, we need to change its velocity again to adapt it to the orbit of the red planet. If we don't do this, the ship will continue in the elliptical transfer orbit. To know how much boost we need to apply to the ship in both points A and B, we need to know the orbital speed of Earth and Mars, but also the orbital speed in the perihelion and aphelion of the transfer orbit. In a circular orbit, the total energy of the ship is given by where we substitute the orbit velocity here. In a similar way, for an elliptical orbit, we can find that the total energy is given by this expression here, where remember that A is the semi-major axis of the ellipse. Knowing these energies, we can calculate the velocity change required to leave Earth's orbit and to leave the transfer orbit. May science be with you.